So now we're going to look at lines in Rn. Okay, so you may think, oh, we're just going to extend what we saw in the previous video to lines in R3 and R4. We are, but we'll see that that will not give us lines. So instead, to define lines in Rn in general, we'll adopt a way to look at the line that was presented at the beginning of the previous video. And that's where you have a point P0 and that's part of the line, and a vector V that's pointing in a direction parallel to the line. Okay. So this is what I drew here. So of course V, you could translate it and put it exactly so that it starts at P0. You could do that. Okay, that's the same vector V. Okay. And imagine, I don't know, the origins here. So what we're trying to describe are any point P that's on that line. So P, X, Y. Okay. So that point P, I can associate to it a vector that starts at the origin and ends at P. It would be that vector here, right? And that vector would have the same coordinates as P. So instead of looking at P as a point, we're going to look at it as a vector. That's why I'm going to write the vector OP. OP is the vector that starting at the origin, ending at P. So, but OP, you can also think of it as the point, right? So it has the same coordinates as point P. Same coordinates as point P, right? So by describing OP, I'm also describing P. So OP is what? So to get to OP, what I can do is instead, let's take a path that I know. I can go from O to P0. I know how to get there because I have the coordinates of P0, and I know how to get from P0 to P. Because all I have to do is move along V. So to get to P, I'm going to start at point P0. Okay, so that's the vector that point P0 has the same coordinates as the vector OP0. And to get to V, I'm going to need to add a multiple of the vector P0P. So lambda is a scalar here. It's a multiple of something that multiplies my vector P0P. So of course, for the right lambda, I'm going to be able to get to P. So if you give me some point P that's part of the line, I could tell you what the lambda is exactly. Okay, so if I expand this, all OP is xy, OP0 is x0, y0, lambda is some parameter that I can vary, okay, and P0P as, yeah, I don't know what P is. I made a small mistake. What I meant by P0P is the vector V instead. Okay, let me erase this. Sorry about that. So it's V that I need to put there. So I know the coordinates of V. I don't know what P is, but I know that if I move parallel to V, so if I multiply that V by some scalar, I'm going to be able to get to any point P that's a part of the line. Okay, so this is why here I wanted to write lambda times V1, V2. Okay, that's better. So that's called that's the vector form right there. Vector form of a line. Just like that. Of course, I could also write it like this. Just look at the x coordinates and the y coordinates, and I'll get this. To me, that's still the same equation. So this is a set of equations that describes exactly this. That's exact same as this. The book calls it differently, but really it's the exact same thing. It's called parametric form. So if you read vector form or parametric form, to me that's the same thing. So if on an exam you answer with one or the other, I don't care. In the book, they care of a line. Okay. So example, if I have something written like this, xy equals 1, 1, 3 plus lambda. Now lambda I didn't specify, but lambda here Lambda is any real number. Okay. If lambda is positive, you're going to end up with points that are here on the line. Okay. Because you're going in the direction of v. If your lambda is negative, you're going to end up with these points because you're going to be moving opposite to the direction of v, because you're going to go against, you're going to have a negative multiple of v. So let's say minus v will take you here, for example, minus a half of v will take you there. Okay. So if I write this, 5 minus 4 minus 5, like that, okay, that would be a line passing through 1, 3, and parallel to 4 minus 5. So this, there you have it. Line passing through 1, 3, parallel to 4 minus 5. Okay. Here's another example. We were going to put the line 2x plus y plus 2 equals 0. I want to put this into vector form. Vector form. Okay. So how do I do that? What do I need? I need a point on the line. Okay. How could I get a point on the line? Well, I could replace x or y by my favorite value, so for the other variable. So here I'm going to be lazy and let's say let y equals 0. Then 2x plus 2 is going to be equal to 0 in that case. So that means x is going to be minus 1. So minus 1, 0 is a point on the line. So therefore, minus 1, 0 is part of the line. So I need that, right, for my point slope form. And then what I need is a vector that's parallel to the line, right, pointing in the direction of the line. So since with that equation, I can get easily a vector that's perpendicular to the line. I just need to look at the coefficients of x and y. So since n equals 2, 1 is perpendicular to the line, okay, so I've got this vector n that's perpendicular. I need a vector that's parallel to the line, but it's going to form a right angle with vector n. So that means that v dot product n is 0. So I just need to find a vector v, any vector v that's whose dot product with n is 0. So can you do that? It's very simple. You just have to flip those coordinates around and hit one of them with a negative sign and you're done. Okay, I could have hit also 2 with a negative sign and that works also. Okay, 1, negative 2 is also perpendicular, and of course any multiple of v is also perpendicular to n. Well, okay, so then v is parallel to the line. Okay, so the equation is, now that I have my two ingredients, it's xy equals to my point, what is it again? Minus 1, 0, plus a multiple of v, where lambda is any real number. I could have added this here, by the way, up there. Here, lambda is any real number, right, when we define our line. So that's it. That's you could also write it in this form: x equals minus 1 plus lambda, y equals 0 minus 2 lambda. And by the way, you can check that this works. How do you check? Well, if xy is, if it works for any lambda here, right? Lambda is any real number here. It means that if I replace so I get basically a point, right? So if I look at this point, right, that's xy, right? That's another way to write down my parametric form, my vector form for that line. So that point, no matter what lambda is, it's going to be part of my line. So if I replace this into my equation here, it should work. So I could check that it works. Like 2 times x plus y plus 2, that should be 0 ultimately, no matter what lambda is. So it means that lambda is going to have to disappear if I'm going to get a constant here. There's no lambda there, right? So, and the constants should all cancel out. So let's see, if I expand this, I guess minus 2 plus 2 lambda minus 2 lambda plus 2. Well, take a look at that. All the lambdas are going away, and the constants also cancel, so I just get a big 0, and it works. So what I have here is something that's close to point normal form. I could write in, I can easily get a normal vector with that form and a point passing through the line, put it in point normal form. From there, I could put it in vector form. And you could also have, there's another form, right, that maybe we shouldn't forget. But if I have something like this, I can put it in point slope form, which is the form we use in calculus. If I write it like that, actually it's in slope intercept form. Slope intercept. Because that's the intercept. The intercept is the y-intercept, remember? And the slope is -2. So I get my y-intercept, 0, 2. And the slope here is -2. But often we'll be working, so this is correct, but we'll be working with lines that are not necessarily in R2. So this interpretation, like putting in slope intercept form, we won't do that in this course. Okay, so we'll really focus on point normal form and vector forms for lines.